Okay, hello and welcome. It's SFU Math 152, Calculus 2. It's Brenda. This is section 11.9, representation as functions, representation of functions as power series. We've been working to develop our intuition. It's a really strong skill to get. This famous scientist discovered the polio vaccine. I guess vaccine is a topical subject right now, July of 2020. Okay, what we're going to see is a continuation of what we were discussing last time, and that is we can see functions in a different way. So we first saw the infinite series with numbers, and we saw that as adding up lists of numbers, and we saw that in fact we could put a variable in there, and that allows us to see the infinite series as a function. And what we now want to do is say, if we get given a function, can we then figure out what power series we could use to represent it? So we're thinking of taking a function, and we're going to start with this one right here, and we're saying to ourselves, can we figure out an infinite series that we could use that would be the same, would produce the same values for x that this formula here produces when x is within the interval of convergence for the power series that we find. So, and the question to this is yes, and that this is a hugely powerful tool in general. So we're going to look at it in one way in this lecture by basically by being able to manipulate the geometric series and using that information to get additional power series for functions. And then coming in the next lecture, we're going to see that given an arbitrary function, so long as it satisfies some fairly non-stringent conditions, we're going to see that we can in fact generate the Taylor series, which will be an infinite series for whichever function we would like. It's a remarkable result. It's an important result, and I would guess, I don't know, in this course that would be one of the two most important things. Perhaps we saw the fundamental theorem of calculus. That is a hugely important idea in this course, and then this idea that we can represent functions as infinite series and that we can do so methodically for the most part, and form a Taylor series is the second most important thing in my opinion. Okay, so we're going to take a look at this function here, 1 over 1 plus x. And then what we're going to do is take a look at the geometric series, which is not exactly this, but we are going to be able to see how to make substitutions. Consider the geometric series. Okay, we know the geometric series looks like this: 1 plus x squared plus x cubed plus dot dot dot, and that can be written like this: the sum n equals 0 to infinity of x to the n. And we also know that that's something there, and we know that if we have this condition, the absolute value of x is less than 1, then we can write a closed form solution for this, x to the n, as being 1 over 1 minus x. Okay. So we have two different representations of a function. For example, we could call this function the geometric series g of x, and I could say to you g of x is equal to this, and it would be equally valid to say to you g of x is equal to this, with the constraint that make that a little bit neater, with the constraint here, with domain absolute value of x less than 1. So if we're going to represent g of x in this manner, we can only use that when this power series converges. It doesn't make sense to use it when it doesn't converge. So and these two things will be equivalent under this condition. For example, I could calculate g of 1/2 I think I've already done this one, so let me do something else. G of 1/3, and I can calculate that as being 1 minus 1 over 1 minus 1/3, which is 2/3. So this is 3/2. Similarly, I could say then the sum of n equals 0 to infinity of 1/3 to the n. That is G of 1/3 as well. And then I could write that out 1 plus 1/3 plus 1/9 plus 1/27, etc., plus dot dot dot, and that I could take successive partial sums and I would see that those converged to 3/2. So I can evaluate G of 1/3 either way. I cannot, so careful, okay, so careful here. Notice if I take something like this, x equals 5, I can calculate G of 5 in this manner, 1 minus 1 over 5, like that, and I'm going to get -1/4. Okay, it does not then make sense on the other side here to go like this. Well, this would be, if I looked at this sum, n equals 0 to infinity of 5 to the n, I would get 1 plus 5 plus 25 plus, etc., 125 plus dot dot dot. I'm not going to claim, at least in the constraints that we're looking at here, that this is equal to -1/4. Okay, so these two function representations for g of x that we have will give you the same number. These two, they will give you the same number when we are within the interval of convergence for the power series. Outside of that, we're going to have trouble understanding how this and this are related to one another. Okay, so that is a key a key thing to be aware of. Okay, so we've got this equivalence between the geometric series, its closed form representation here, and its power series representation here. Now we're going to ask, can we do that for some other function? And the other function that we are asked about right here is f of x, which is 1 over 1 plus x. So what I do is I think of this in this way so that I can use my previous knowledge. I'm going to think of it like this, and then I say, oh, hey, this is actually a substitution. So I can then write this in this way. So I see that this looks like 1 over 1 minus something, when the minus something is this. And so that will then be the sum from n equals 0 to infinity of minus x to the n. Because normally if it was a geometric series, this would be just x, but that is minus x. And so then I can rewrite that like this. So now if I just want to write out the first few terms and see what that looks like this. Okay, it goes like that. Okay, similarly, the domain will be the same as it was for the geometric series. Okay, so I then, just to write this out formally, 1 over 1 plus x is exactly equal to the sum of n equals 0 to infinity of -1 x to the n for the absolute value of x less than 1. Okay, so I use my information of the geometric series, and then I saw how I could make my new function look like a geometric series, and then I see what has to be there, and I make that substitution. Okay. So if we have I being the interval of convergence of some power series, and then we consider any value of x within that interval, then we call that power series f of x when x is in that interval. We're really clear about that. Then we call this thing here the power series representation of f of x. Okay, so let's see if we can find the power series representation of the following functions. So in the back of our mind here is what we're thinking is starting from the geometric series, which we know the power series representation of. So we know this to be the case. Okay, so we're starting from that position. While you're doing these kind of things and practicing and getting used to this idea, you can check with Wolfram Alpha. So you could go into Wolfram Alpha and, for example, we're going to do this question A. You could go into Wolfram Alpha and say power series, just type this in, power series for 1 divided by 1 plus 4x hat 2, like that. And then that will allow you to, well, give you the answer, and then you can check what you're doing. That's a big believer in checking your answer. Right after you figure something out, you check, and then you're like, okay, I got it, or, oh, something went wrong, and then you sit there until you figure out what that is, and then you really learn something. Okay, so we're going to try to find the power series representation for part A there, f of x. So what I'm thinking is, I'm thinking of starting with the geometric series, and so I'm going to look at this here. I see 1 over 4, the function I want to find the power series for. I could rewrite that like this: 1 minus minus 2x squared. Okay? Because that is the same as 1 plus 4x squared. And then I see that I have this form here. I have this form here, 1 over 1 minus something, 1 over 1 minus something. And here, what is the something? Well, the something is this. Okay. So now I'm going to substitute that into my power series. So I'm going to claim then that this thing here is going to be equal to the sum of n equals 0 to infinity. And for this x here, I see that that matches with this x here, so I'm going to match that with this here, and I get here minus 2x squared to the n, and then I do a little bit of algebra here, and I get minus 1 to the n, 2 to the 2n, x to the 2n. Okay, so now I have a power series representation for this function. I need to worry about for what x's does this converge. So now I have this. I've got a couple of options. I could use the ratio test to find the radius of convergence. Okay, that will always work. Or I can also look at it this way, that I know that my x here, it needs to be less than 1, which means that my x here has to also be less than 1. That common ratio has to be less than 1. So I simply take a look at that. That has to be less than 1, which means that 4x squared has to be less than 1, which means that x squared has to be less than a quarter, which means that the absolute value of x has to be less than 1/2. Okay, so I have a radius of convergence equal to 1/2. And I have an interval of convergence that I can set up, but I do need to be careful about the endpoints. Okay, so I can set up a interval of convergence. And I will get, I will initially at least get this minus 1/2 to 1/2, and then I'm going to worry about what happens at -1/2 and at 1/2. And I can see actually quite quickly, just by looking here, if I put in 1/2, I'm going to see that these two things cancel one another out, and I just get this -1 to the end. That diverges. And then if I put in -1/2, same thing happens. Okay, so because I've got a square there, so I see that the endpoints do not converge. So I just check that quickly, and I see that my interval of convergence is what I've listed there. Oftentimes we often just ask for the radius of convergence, and we don't worry about the endpoints unless we're specifically going to know that we're going to be using the function right to the maximum edge. If that's not the case, then we just usually report the radius of convergence. Okay, let's take a look at the second question. It's a very similar style. So g of x, the second problem, g of x, it looks like this, x over 9 minus x squared. So I'm going to write that like this. I'm going to factor out that x in the numerator, and I'm going to write this as 1 over 9 times 1 minus x over 3 squared. Right? Because I want to see that in that kind of form of 1 over 1 minus something, and then maybe I'll even just get that 9 out in the front like that. So this is an algebra problem to make it look like the form of a geometric series. So there it is there. So now I can immediately write what the power series representation is for this, and that looks like this: x over 9 times the sum of n equals 0 to infinity of x over 3 squared to the n. Okay, that is, I am taking this thing right here, and that is going right here. Okay, so we can then move this here into the inside because it is independent of n. So no trouble moving something in and out of the sum if it is independent of n. So be sure that you feel happy about that. Think about it. That's an important thing. So I move that in, and then I rewrite this thing, and it looks like this: the sum of n equals 0 to infinity, x to the 2n plus 1, and then that is divided by 3 to the 2n plus 2, and that is equal to x over 9 minus x squared for some values of x. And let us figure out what values of x those are. Well, that the geometric series converges when its common ratio is less than 1. So I'm going to solve this equation here. That would be x squared less than 9. So that would be the absolute value of x less than 3. So I would have here the radius of convergence is 3. So r is equal to 3. And I would be at a first pass the interval of convergence minus 3, 3. And then I would need to check endpoints. And I'm seeing when, let's see, when x is 3, I have 3 to the 2n plus 1 divided by 3 to the 2n plus 2, so I have 1/3. So I add up 1/3 plus 1/3 plus 1/3 plus 1/3. That is going to diverge. As I could just basically factor out a 1/3, and then I'd be adding up ones. Okay, so it's not going to converge. And then when I have the minus 3, let's see what happens. I have, I'm going to get positive and negative 1/3, which is also not going to converge. Okay, so the interval is as I've stated there. So you have to check the endpoints. Okay, so that's one way, a substitution on the geometric series. And that also what we can do is we can take the we can take a power series, this is the general form of a power series here, and it will have some radius of convergence. Then what we can do is, well, the theorem is telling us that the function defined by this power series, it is differentiable on this interval, the interval between well, a minus the radius of convergence and a plus the radius of convergence, and that we can differentiate term by term. That's what this is telling us. We can go and take derivatives term by term. We can take the derivative term by term in the infinite series. Similarly, we can take the integral of that power series representation of f of x, and we can integrate term by term. And both of these new series will have the same radius of convergence. Okay, what I'm going to say here is this is a true statement. It's a theorem. We're not proving it, but it is a theorem. But note that the interval of convergence could be different. May be different. Okay, and so that is basically the endpoints. So you would need to check the endpoints. Okay, so let's use this and see how we can be clever about finding the power series representation of the following functions. So we'll start with f of x. So we get told that f of x is this function here. And we want to know what is the power series representation of that function. So what you do is you look long and hard at this, and then you think to yourself, oh, hang on, it occurs to me that the derivative with respect to x of 1 over 1 minus x is 1 over 1 minus x squared. And I know the power series representation of this because that's the geometric series. So that means if we know that this thing is the derivative of the geometric series, then if I take the geometric series and here, so let me just put it in symbols, might be easier. Here's then, okay, just got the low battery indicator. Hang on a sec, I just got to plug in my laptop. Sorry for the delay, just a momentary pause while I plug it in so I don't die during this thing. Okay. All right, I've got the battery plugged in. Sorry about that. Okay, here we go. So I'm saying here that the integral of f of x dx is equal to 1 over 1 minus x. I mean, that you can see that falls right there like that. And I know what the power series representation of 1 over 1 minus x is. That is the sum from n equals 0 to infinity of x to the n, like that. So therefore, I can, if I take the derivative of this and the derivative of this, I will find here that f of x is the derivative with respect to x of the, so I'm taking the derivative on both sides of this infinite series here, x to the n, and that is equal to the sum from n equals 0 to infinity of n times x to the n minus 1. Then we started with that geometric series. So for this series right here, the radius of convergence is 1. And so also for here, the radius of convergence is equal to 1. So I've found the power series representation of this function here. What I'm saying is I've been able to, by noticing this relationship between this function and 1 over 1 minus x, I can now tell that this is a power series representation for 1 over 1 minus x all squared, and that the radius of convergence for that is 1. Okay, certain amount of thought, certain amount of seeing the relationship between series that you know and ones that you've seen before. Yeah, and then let me just as sort of maybe a bit of an aside here. Imagine I pick some value of x like I don't know, a half or something like that. And I was wondering, here let me put x equals to a half on this side. This would be looking like this, n equals 0 to infinity of n times 1/2 to the n minus 1. And then when n is 0, this thing is 0. When n is 1, I get 1. And then when n is 2, I get 2 times 1/2 to the 1. So this one here was when n is 1. So that was 1 times 1/2 to the 0. And then I get 3 times 1/2 squared. And then I get 4 times 1/2 cubed, 5 times 1/2 to the 4, and it keeps going. Let me just, maybe this looks like this: 1 plus 1 plus 3/4 plus 4 eighths plus 5/16 plus like this. So I'm thinking, so this is like 2 2s. This looks like this, if you would. 2 2s, so follow the pattern. 2 3 4 5. Looks like this. 1 over 1. 1 2 3 4 5 in the numerator. 1 2 4 8 16. So if I was to have this be, and I would say to be asking myself, I wonder what this adds up to. I would be kind of stuck, really, looking here. But having been able to do this, and more importantly, having been able to do this, I can then say, hey, but I can do this. This looks like this: 1 minus, what is x? A half, and that's squared. So that looks like this: 1 over 1/2 squared, and then that looks like this: 4. So this thing over here is going to allow me to actually figure out what this sum is in this case. Okay. It's not a geometric series anymore, right? Because we don't have a common ratio. But because we've been able to go through this relationship and figure out what function this does represent in this form, then we can come to the sum. Okay, let's take the next example. That is, which one? G of x. We're going to try to find g of x, power series representation for this function, the log of 1 plus x. Okay, so the thing to do is be looking at that, and you want to recognize as the integral of 1 over 1 plus x. And we already found what that was. Now, or you could go through the procedure again to find out what the power series for this is using the geometric series, but we did just find that. So we already know that 1 over 1 plus x is equal to this sum here. N equals 0 to infinity, minus 1 to the n, x to the n. Okay, so then I can simply integrate on both sides. So then I would say then that's fine. Then the integral of 1 over 1 plus x dx is equal to the integral of the sum of n equals 0 to infinity, minus 1 to the n, x to the n, like that, dx. And then I'm going to integrate on this side, getting that function that I wanted, the log of 1 plus x. And on the other side, I'm going to switch the summation with the integration. So I'm going to now go here, like that. We are permitted to do that via that theorem above, so long as we are within the radius of convergence. So I then perform this integration here, and I find that this is the sum from n equals 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1. And that is the power series representation for this function right here. And the radius of convergence is equal to 1. We started with a radius of convergence of 1 here, r was equal to 1 here, and that is preserved as we go through with the integrating. So now I managed to find a power series for the log function. Okay, there's one more example to do here. That's the arctangent. What is the power series representation of the arctangent function? So we have, I'm going to call the arctangent function h of x, but this is arctangent x. So we want to know what is the power series representation of that. So the first thing I'm going to note is that if I were to take the derivative, I would get this function here. The derivative of the arctangent is this here. Okay. Oh, that makes me feel good because I recognize immediately that I can get a power series representation for this via substitution on the geometric series. So then this looks like this. That. Okay. So I can then immediately represent that this way here as this power series here, which, as I have been and will typically do, move the minus 1 separate like this, and x to the 2n. And right now I'm here, I started out with the geometric series. The radius of convergence is 1. So I'm sitting here with a radius of convergence equal to 1. And let me just put what I've got here in the first step here, h prime at x, which is my which is the derivative of the arctangent, 1 over 1 plus x squared. I now have a power series representation for that, looking like this. Now I want to know what is the power series representation of h of x. Well, h of x is clearly the integral of h prime of x. Okay, and so that is the integral of 1 over 1 plus x squared. That's the arctangent function. That's where we started. So then, therefore, I'm going to keep going with this. I mean, I've got a whole series. I've been going through. I've integrated this to get that. I then integrated. I wrote that out twice. Then I integrated that. Now I'm going to integrate that. So I'm just going through and integrating all three parts here. And so that then will be the integral of this power series here, which looks like this. There it is, like that. Okay, so I've integrated all sides, and then that I can do, I can either do it term by term, or I can just do it directly. So let me just do it directly from here. I'm integrating that there, and that's going to give me the sum n equals 0 to infinity of minus 1 to the n. And then when I integrate this, I get x to the 2n plus 1, and then I'll need to divide by that 2n plus 1 to keep the coefficients correct. So there I have my power series for the arctangent function. The other thing I could do is when I'm doing this integral here, I could do it term by term and then put it back together. I'll show you what I mean. So I've already got the answer, but let me just show you this. I could say, okay, I've got the power series for this thing. Let me write that out. 1 minus x squared plus x to the 4 minus x to the 6 plus x to the 8 minus, and it keeps going. Okay, rather than using the summation notation. And then I could go term by term, and I would get here x minus 1/3 x cubed plus 1/5 x to the 5 minus 1/7 x to the 7 plus dot dot dot. And that that is my arctangent of x written out term by term. Sometimes I like to write them out term by term because I find it easier to visualize. But this is exactly equivalent, of course, to this guy here. But I'm going to show you something kind of neat when you're looking at this. Okay, these are equivalent. So I've got now a power series for the arctangent. Now just imagine myself computing the arctangent of 1. Okay. That would be like this: 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 11th, etc. Right? Because I substitute in x equals 1 right here, and I substitute in x equals 1 over here. What is the arctangent of 1? Folks, that is pi by 4. So that means that pi by 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 11th. How cool is that? So in fact, we have a way of calculating pi right now. We could do this thing over here, multiply by 4, and we can get an approximation for pi. And I think it's so neat to see pi come up like this as a sort of alternating sum on the odd numbers. And we saw pi come up with we saw this one. We saw pi come up here. Plus 1 over 2 squared plus the reciprocal of the squares. 3 squared plus 1 over 4 squared plus dot dot dot. We saw the pi come up there, sort of pi related to the square numbers. Now here's pi coming up again like this, alternating sum on the odd numbers. This converges very, very slowly. It's not practical to calculate pi this way because you add and subtract and add and subtract. You go on for quite a long time, and you only have 1 or 2 decimal places of pi. So you could actually check that out with a little computer program if you can write one fairly quickly, and you could just try adding the first 100 terms and seeing how many decimal places of pi do you have. Try adding the first 1,000 terms and see to yourself, boy, this is not a good way to figure out what pi is. So we don't deal with speed of convergence in this class. The sort of probably the place where you would see that first would be in Macam 316 and in numerical analysis. But clearly when we want to get results, we would want to try to get them with the minimum number of calculations. Okay, so now what we've done is we've used our knowledge of the, I want to just go over the method here. So we have the geometric series. Like that. We have the geometric series, and we understand this. And then what we have done here is we've used the geometric series to find other power series. To find, let's put it this way, to find power series for other functions. And we have basically 3 methods of doing that. One is substitution. So that was substitution. That was when we would have something like this, or we would have something like this, or we would have something like this. It doesn't matter. Let me just put like this. Any of these kind of flavors where you can see that you can substitute something here. You have 1 over 1 minus something, that then you can make a substitution. So that is one method. We saw that we could use differentiation. And we saw that you can use integration. Okay, so we have we now have the ability to expand which type of functions that we can find power series representations for. This is fast to do. We're going to get a much more algorithmic way to do this in the next lecture. So you won't be thinking, oh no, what if I don't see what to do? What if I didn't notice that the log of 1 over 1 plus x was related to the geometric series? What if I didn't notice that? I'd be sort of just sitting there not able to do anything. What we're going to do is get a much more methodical method coming in the next lecture. However, if you do get to sort of see a clever substitution, or you can see that you can quickly integrate or differentiate to get what you want, it's actually quite a bit faster than the methodical method. So pausing and saying, can I be clever here, is good. And if you say, can I be clever, and the answer is there's not a clever thing to do, and or I didn't see the clever thing to do, then of course you'll be able to go with the methodical method. But this sort of some interesting results coming here. All right, that is all for section 11.9. I will be back. Thank you. Bye.